move this vector and then become parallel and hit here. Okay, and we know that if you draw like this up, it's going to become V2 plus V1. We don't want. We want it to be minus. Okay, minus. And how long is that minus? Here. This one is minus V1. Okay, this is our V1. This one minus V1. Why? It's parallel. Okay, it's parallel but opposite direction, so it becomes minus. So when you have V2 plus negative V1, it becomes V2 minus 1. So that means from this point go to this point here, this one is the changes. Okay, that one is the changes. The green color one is the changes in velocity. Okay, the changes in the velocity. Now look at that direction. The green one is actually pointing in this direction here. You might realize that it is not passing through the 0 here. So why? Because your angle is huge. The angle is big. What happens if we reduce, we make the delta t become shorter and shorter? We repeat the drawing, the p become nearer and nearer. Sorry, this one is not p, this is q. Okay, q. So we repeat by moving the q nearer and nearer to p. That means we make the analysis based on a shorter delta t value. So that means when your theta is become smaller, your green line is going to become nearer and nearer to O. Alright, so we can make an analysis now. Okay, our delta t, delta v, which is equal to what? Which is actually equal to in this diagram is equal to your this value. Okay, this value minus v1, and then we observe that. Okay, observe that the delta v pointing, okay, towards O if theta is very, very small compared to 1 radian. Okay, it's very, very small compared to 1 radian. So we have this. If you have delta v divided by delta t, you have something that we call the acceleration. Okay, so this is the acceleration that is actually pointing very close to the center of rotation. So we call this one the centripetal. Okay, centripetal acceleration. Alright, centripetal acceleration. So to simplify, we normally use AC. Okay, centripetal acceleration. So our centripetal acceleration is equal to this one against t, but other than that, we can also put this one as something else, because we know that delta v, okay, it has a relationship with omega. So that means other than that, you can also have another formula, because since r cannot change, so we have what? We have something else. Okay, we have something, maybe it is something like r, this one is our delta omega over delta t. So this might be another possibility to get the equation. Alright, so from here, we're going to end up with a formula to calculate our, what we call that, the angular, centripetal acceleration. So from analysis, it ends up to be AC equal to V square over R. Okay, it ends up as V square over R. Alright. So later we're going to look at how we end up with this equation. Okay. Okay. Now, how do we get this from here to here? Then we have to look at two things here. We are going to separate the real diagram from the velocity diagram. Okay. So first we look at the diagram of the motion of the object from P to Q. All right. Okay, now we start with this diagram. Object is moving from P to Q, right, in a circular motion, right? In a circular motion like this, okay? And the angle here is theta, center O. This is P, move to Q. And then if you look carefully, this motion here is the arc. Okay, this is the arc. So this arc here, I will call it delta L. Okay, delta L is related to this one. So your delta L is related to this one, equal to R theta. Remember that? The S here equal to R theta. So this is our equation number 1. Okay, this is equation number 1 here. Now next one is we want to know the velocity. So you see our first of velocity is in this direction. We draw this. So that means the way I draw the direction of the velocity is referring to this diagram here. Okay, referring to that diagram here. So our V2, let's say, is in this direction. There's our V2. Okay, our V2, I enlarge the V2. And then my V1 is in this direction. See that? According to this one, this is my V1, which is actually negative V1. Okay, negative V1. And I have these changes. Okay, this is the changes. This one I will call delta V, the changes, right? And this angle, mind you, is the same as theta. Okay, it's the same as the theta. Now, these two velocity, negative V1 and V2, they are velocity, but their magnitude are the same. Okay, I'll just simply call V, which is the speed, because when object rotate in circle under constant omega, what happens is their speed is the same all the time in a circle, but only the direction changes. So if direction changes, we call velocity changes. But under this condition, we only want to take the magnitude of the velocity, V1, V2, or whatever V you can talk about, but the velocity is a speed. Okay, magnitude is a speed. So now we can find the relationship. Okay, the relationship, we know that the theta are the same, and we know that, what is this? This delta V magnitude is actually equal to the magnitude of either one of them, which is V multiplied by theta. Okay, now do you get the relationship correct now? We can actually divide them, right? I will call this one equation number 1. This is equation number 2. So I can use number 2 divided by number 1. You have delta V over delta L, which is equal to V over R. Okay, V over R, right? V over R. Now the next thing is, if we move this thing over here, your delta V over V, okay, the delta V over V, and this one become delta L over R. Okay, delta L over R. What is this thing now? Okay, what is this thing? Don't see it. Okay, maybe we don't look at it that way. Okay, we change the condition, we leave it like that. Maybe easier for us to analyze the equation further. Okay, so we will move this one over to this side. Okay, delta V is equal to V over R, and this one is delta L. Okay, now how are we going to change this side here so that it's related to A, our acceleration? Okay, so if you look carefully, if we divide both sides by delta T, which is the time taken for the object to move from P to Q, delta T. So that means when you divide, you're going to delta V divided by delta T is equal to V over R, delta L over this, delta T. So the changes of velocity divided by changes of time is our acceleration, and then is equal to V over R. The changes in the displacement divided by time is actually equal to your velocity. Okay, so your A, centripetal acceleration, it end up as V squared over R. Okay, so that's where we get this equation. Acceleration is centripetal acceleration is equal to V squared over R. And then we also know that, but We also know that V is equal to R omega. So that means our second formula for centripetal acceleration is equal to R omega square over R. So that means our AC is equal to omega square R. That is another equation for our centripetal acceleration. Okay, centripetal acceleration. All right. So that is the way we derive. You must know how to derive this equation. Okay, there are a few equations you need to know how to derive for this chapter. Okay, the next one. Okay, the next one will be our 5.3. Okay, 5.3, which is the centripetal force. Okay, 5.3 centripetal force. Okay, centripetal force, I'll call it FC. Now, knowing Newton's second law. Okay, from Newton's second law, F equal to ma. Since the net force is equal to mass multiplied by acceleration, any object that is experiencing acceleration must have a force. Okay, must have a force. So this centripetal force is equal to m multiplied by v squared over r, which gives us mv squared over r. Or if you are using the second equation here, you're going to have Fc is equal to m omega square r. So we have two formula to calculate the centripetal force. Okay, so since your centripetal acceleration is actually pointing towards the center O, so that means your centripetal force doing the same thing, because these are vector. These are scalar, scalar, scalar. So the only vector that you have is this one. So the force always follow the direction of your acceleration. All right. So that is our centripetal force. So centripetal force, you don't have to derive. You simply replace the centripetal acceleration into the formula for Newton's second law under special case, which is dm dt equal to 0. So we assume that the object rotating in circle does not change its mass. All right. So that is our chapter the last part of our chapter number 3, 5.3, which is a centripetal force. The difficult one is from this. Okay, from here. Okay, centripetal acceleration until you get these two equations. All right. So the next part, this one easy. But when we talk about centripetal force, there are two applications for two conditions in which it is applied. Okay, so now we look at 5.4 application of centripetal force. Okay, centripetal forces. So we have two ways in which we apply that two conditions. Number one is horizontal centripetal horizontal circular motion. Okay, horizontal circular motion. So for our horizontal circular motion, for example, okay, example will be something like this. Okay, example is a piece of stone tied to a string and spin. Okay, and it is spin in a horizontal circle. Okay, in a horizontal circle, something like this. Okay, so you stand in the middle. This is a stone, and this is where your finger holds. So the stone is actually moving like that. Okay, so you do some sort like a horizontal circle, and you realize that you need to pull the rock. You need to pull the stone. If you let go, someone is going to get hurt. For example, if you swing this one around in your classroom and suddenly the stone fly away from the string, is snapped, then you have a lot of answer to question to answer. Okay, so now what happened here is this stone can move in a circle, which actually is accelerating, need a force, and that force is supplied by your hand. at this in this direction. So the tension in the rope is the one that supply the centripetal force to hold the stone in a circular motion. Well, this one apply to all type, okay, all type of horizontal circular motion. Well, sometimes it's not really that easy to see. For example, if it is in a circus, you might see people actually moving in a cylinder. Okay, in a cylinder. For example, this is a cylinder, huge cylinder. Okay, huge cylinder where you have actually motorbike moving inside. Okay, motorbike moving inside here. Okay, the motorbike moving inside the huge cylinder. So how can this motorbike move in this huge cylinder? If we see from the top, okay, this is where the motorbike actually moving. Okay, it's moving in a circular motion around the cylinder, and the cylinder is straight. So that means something is holding that motorbike so that it moves in a cylinder, in a circular motion. So one of these is the centripetal force, the normal reaction. Okay? The normal reaction, the combined normal reaction from the what we call that, from the, okay, the normal reaction from the contact point between the tire and the wall of the cylinder. So that is where the forces is existing. Okay, so of course you cannot just move really horizontal. You can see that the motorbike actually is slanted. Okay, this is the wheel of the motorbike. Okay, so you can see that the rider, okay, this is a rider. The body of the rider. Okay, it cannot be me lah. It can be either Lawrence or Thomas Key here. Okay, the rider, okay, is riding a motorbike. Okay, now this rider, you see, is not totally horizontal because there are some other forces involved. First, we know that this is the normal reaction, and then don't forget Thomas or Lawrence, they have the weight, right? They have weight. So the weight is here. So what is holding them? Okay, if they are riding like this, definitely they will fall down because nothing else to support them. So they need to ride at a certain angle, not like this. So that means if they are riding like this, this is a disaster. So they need to ride in some other manner. So that means to compensate the weight coming down, they must have something else to balance them. So they need to ride in such a manner that the motorbike is actually tilted up a little bit. This is a tire of the motorbike. Okay, and this is how okay, so now draw the same diagram again. So we have this normal reaction, and then we have weight. Okay, we have weight down here. You see the weight is going downwards, and you have something else, which is the friction. See, the friction and this one had been compensated. Okay, compensated by each other. So they are compensated so that at a certain speed, you see that the slower they cannot be too slow, because when they are too slow, they will plunge down because of the weight itself. So this one is possible. Okay, this one is possible, but of course, say is easier than done. So this one is possible, but of course you need to like practice to get yourself used to that rotational motion. All right. So that is our horizontal circular motion. Okay. Now, this type of for this case is very easy to solve the problem. Okay. Now, what we want to know is we want to know the magnitude of the centripetal force here. So in this case, the magnitude of our centripetal force, okay, this one, the centripetal force is equal to the tension, okay, in the rope, which is equal to the mass of the stone multiply by how fast you're rotating the stone, divide by the length of the string here. Well, this one is everywhere the same. They're everywhere the same. But of course, the direction is different. The direction is always from different location. Your force will be different direction. But the magnitude of force is always mv squared over r. Now, this one is a little bit more complicated, but it's still the same. Your centripetal force is the same as the normal reaction from your motorbike. So you have to know how to get the normal reaction in this case. Alright, so this one is more complicated than this one. Okay, so that is our second example for horizontal circular motion. Now, come to the next one, which I think you experienced it before when you are driving your car in a roundabout. So that is our next one. This is page number 3. So go to page number 4. Moving your car, driving your car in a roundabout. So I'm going to draw a huge roundabout here. Okay, and this is the center of the roundabout. Of course, you're driving too fast, you go straight up instead of passing through the roundabout. So this is the road to and fro. Okay, to and fro. Alright, so this is the divider. Okay, so that is our divider, like this. So you're not supposed to cross the divider, and this is also you're not supposed to cross. Let's say your car is somewhere in the middle here. Okay, you are moving from here and then go to the other side. You can also turn here and come back, but they're all the same story here. Okay, that is your car. Okay, your car, definitely you need wheels. Okay, 4 of the wheels on your car. Okay, 4 of the wheels on the car, and to move in a circle. Okay, an experienced driver will always have the same moving in, and then started to move at exactly the same path. So you're moving in from here. Okay, so now you see you're moving in straight line here, and then move in, you are following the circle, and then by the time you reach here, you move out. Okay, you move out. So here you have a velocity v, and the mass of the car is m. Now you're moving in a circle. You know, you're moving in a circle. You are experiencing centripetal acceleration. So there's no rope actually pulling you to move around in a circular motion. So it means what? You need something to hold you so that you move in a circle. So the only way to do so is from the friction of your car tire. Okay, the friction. So that means you have how many tires? If you have 4 tires, then you have 4 friction. Okay, 4 friction. I call it F1, F2, F3, and F4. But we cannot analyze them for separate tire because it still depends on whether you are getting faster or slowing down. So all these F1, F2, F3, and 4, they are all different. But we only take the average value. We sum them up, and we assume that they are acting in this direction. This is your average force, which is equal to F1 plus F2 plus F3 and plus F4. So that means our car can move in a circular motion in our circular roundabout is because of only one thing, the friction. Okay, now we want to know how can we find the maximum velocity from our movement of the car in a roundabout. Now let's assume the distance of the car from the roundabout is r. The mass is m. We assume that the human inside there don't shift their position so that the center of mass is exactly at the center. And then the car is moving with a velocity v. So now we want to know what is the maximum speed that the car can travel in a roundabout at this particular distance from the center of the roundabout. So how do we start? Okay, we know one thing, the friction. Okay, our friction is the one that supply the centripetal force. So our centripetal force actually comes from the friction, our average friction. But we know one more thing also. okay, we know one more thing. Our friction actually is given by mu n. Okay, mu n. So that means our centripetal force is given by mu n. But other than that, our centripetal force is also mv squared over r. And our normal reaction, assuming that the car, okay, has a mass m, so it's equal to mg, and we assume that the roundabout is horizontal. Then we can cancel our m, okay, and then we simplify equation. Our this one v become the square root of mu gr, okay, is equal to mu gr. So now it's very clear that the maximum speed that you can travel is the square root of the combination of the mu, the g, and the r. So that means the mu is a characteristic which we call the coefficient of friction. Is a characteristic between the contact point of the tire and the road surface. So you can actually increase the mu value by using a tire that is better, which is softer compound. So soft compound tire are the tire used in racing car. Soft compound means they are more sticky. They become softer when the temperature increase, so that the grip on the road surface is better. That is how you can increase. Other than that, if you want to be able to move faster, you can actually move at the outer lane, so that you can increase the speed. But that actually is not really that is the advantage, because when you move outer lane, even though you are faster, but because your lane are shorter, people can take advantage by using inner lane to overtake you. That is how it happened in racing. You overtake from inside because people thought that they are outside, they can move faster. Well, that is actually a more psychological than the reality. And then what about G? G is the gravitational force, which we gravitational acceleration, which we cannot actually change it, but we can use artificial G. For example, the design of the sports car have something that we call spoiler behind there. So this is our sports car. Okay, this is a sport car. Now, we know that the sports car is designed to be as aerodynamic as possible, but you want to have a larger grip so that they don't spin out from the circle. You can do that by using the inverted aerofoil in front here and also behind here, in front here, behind. So the purpose of the aerofoil is actually to push your car down here and here. This is what we call the G-force, okay? The G-force. G-force in front and the G-force behind. So this G-force actually push the car lower, increase the traction, okay, and also increase the stability of the car so that it can move even faster in the circular path. All right, so that is how we can actually increase the performance of the sports car or even your car. But all this G-force